Hello and welcome to fourth lecture of course on data-enabled tribological engineering from experiment to predictive models. Topic of this lecture is adhesion, abrasion and surface fatigue mechanism. This topic is very vast and it requires many lectures to really cover depth. There are a number of books also on that. However, we try to summarize mechanism in concise manner so that we can cover in one lecture. I'm just trying to refer the four diagrams which I shown in lecture 1. This is a mechanical seal which what we use a carbon graphite seal. We showed this kind of a two body abrasion um, in first lecture. This is a three body abrasion and this is a pitting wear which was mentioned in lecture 1. So this is a pitting wear. And but if we try to concise our topic, we say there is adhesion, two body abrasion, there is a three body abrasion and surface fatigue phenomena. The question comes, why do we study this kind of topic? Main thing is that there is a surface degradation topic, and we know the surface degradation leads to the failure of the function or failure of the system itself. And report says that almost 70% failures happen because of the surface degradation. Now, if there is a surface degradation, naturally there will be huge economic losses. Not only economic losses, but there will be safety issues also, because people are going to get involved in operation and the safety issue will come. So, what is the right approach? In my view, instead of looking at the failure and learning only from failure, we should start concentrating on the faults. What is the meaning of this? We are saying we try to reduce a scale and we are trying to think about the roughness scale, something like a micron to nanometer, that kind of a scale. And if you are able to diagnose fault at that scale, remedial actions can be taken well in advance. So this is what our theme of this course. And if I try to reword my whatever I said, you say there is a need to utilize feedback loop, particularly for product development. So for that purpose, what we really require, we need to understand the failures, and I give an emphasis on the faults which are going to finally lead to the failures. We need to extract the knowledge. Maybe we can document the knowledge, we can convert in algorithms or maybe say tabular form and then utilize whenever there is a need, and implement that knowledge in a product evolution, because we know that product would need to continuously evolve, not only from functional point of view, not only from technology point of view, but environmental sustainability point of view also. So whenever we do something new, we need to conduct the test, and this is a topic which will be covered in the lecture 5th, the conducting test. And then one more thing comes, if we learn from here, there is a possibility of continuous improvement. We continuously can think from thick to thin lubrication. Suppose today we are using a 10 micron layer, can we go for 8 micron, can we go for 6 micron? So that's going to really help maybe continuously evolve the technology. However, we know that there are too many parameters, and that's why we really required a very sophisticated mathematical tool, or what we call a multivariate analysis, and we want a ML algorithm or machine learning algorithm. Why do we require it? Because whenever we conduct the test, we will have only few parameters which will be variable, other parameter will be kept constant. So we will get some results, but those results will not be generalized one. That means those results are only specific location based results, and when we go for the multivariate, we require such a many conducted tests, or maybe whatever the data we have. And that's the beauty of the machine learning. And if you have a very big data, how do we extract the right feature and then make the right models? That's why we require that way. The question comes, we already have done some, or maybe explored some equation of the friction and wear in lecture 3. So why we really require this lecture? If we really require only some equations, we directly go to lecture 5 where we need to conduct the test. Why do we really require this lecture? So there is a need to really understand few mechanisms, And then we say already this addition related to friction and wear has been covered, or maybe to some extent covered. Now coming to the two body abrasion, and we use a word wear, two body abrasion for the wear, but for the friction we use a word plowing. It's not a abrasion we use a word, we use a plowing word, because that's more common for the friction. And if I try to express in this whatever I explain here in slightly different words, what will I say? That several classification of the friction and wear mechanism have been documented. There are many published articles, many published books also. And two fundamental friction and wear mechanism, namely adhesive wear and abrasive wear, adhesion on the friction and then plowing friction, were studied in third lecture. We understood the plowing abrasion occurs when there is a harder surface which is moving through the soft surface, or maybe elastically plastically deforming it, and then finally it may lead into the some sort of wear debris. Now when we say the wear, we need to know what is the meaning of that. We say the wear refer to the phenomena of material separation from a given surface, and it occurs when stresses surpass the material strength, resulting formation of the crack. Consequently, the crack propagates and causes detachment of the material, leading to creation of wear debris. This removal of the material from a surface, which you are using the word surface degradation, causes a dimensional changes and so losses in a performance. Understanding wear mechanism and related friction and being able to predict wear using proper models can lead to better control on the wear, friction and overall economic benefit to us. That's why we really require this kind of a lecture, so that we can understand little bit more about what is a friction, what is a wear, and then how they are related to each other and how they are going to affect the results. For that purpose, let's start adhesive wear, and we say we want to go with a nanoscale observation. Again, as I am using the word nanoscale observation, that means we are going for the oxide layer on top layers, which is a kind of surface roughness level. It can be nanometer, it can be micrometer. Now here we are saying here, in addition generally, that there is a possibility of the electron transfer from a opposite surface to the surface which is shown over here. An interesting thing is that if the surface is clean, then there will be oxide layer, and we have already shown that oxide layer can be in angstroms level to nanometer level. Now major problem comes when there is a rubbing. This is a kind of pin which is trying to rub the surface or on the slide on the surface. There is a possibility of the wear debris generation, and this wear debris generation will be related to oxide layer only. It is not a complete material. We say there is a material content may be much lesser. It can be 20%, 30%, but again this is an extreme level of nanometer level. So this is acceptable. That's what we use the word acceptable wear. This is acceptable to us, but going beyond that, when only the virgin surface, so maybe say surface 1 and virgin surface 2, they glide or slide against each other, then the addition occurs because of the molecular interaction or exchange of the electrons. Then the cold weld junction occurs, and to break the cold junction, either we really require lubricant or there will be a huge wear rate. So these are the things are related. That's why we are trying to interpret the same thing in slightly different manner. Here what we say, the results of the localized stresses, because we know that there will be asperities on the surface, and because of the stress they will go almost 6 to 7 times, and then further the whatever the cold junction happens, it gets to need to get ruptured because of the relative motion. Now where there initially we use a word only the load, but we know the surface roughness is affecting a lot. If there is a oxide layer formation or some sort of chemical, then there is a need to think about the chemical makeups. And then few materials are more prone, naturally they have more surface energy, and there are some operating parameter like a temperature, humidity that need to be considered. So when we are talking about the friction, we are talking of the wear, there are too many parameters. As I mentioned, the most of the test results which we have been documented, they are kind of 3-4 parameters only. We don't get holistic results. And then we can use ML to combine 3-4 different tests in a one uniform manner. That will give a good results. For that purpose, we need to understand first what are these parameters and how they are affecting, what is the relation, so that we can check. Because when we go with a guided practice, we will be able to get a good results. If we go completely let me say without knowledge, material or maybe data will not be able to give a good knowledge to us automatically. Of course, for even artificial intelligence, we need to initiate something, we need to give some direction, so the results are faster, or maybe we are able to quantify it properly. So yeah, that's why here we are saying the surface is particularly weird. We have learned that metals have a generally higher energy, surface energy. That's why the metals are more prone to adhesion compared to polymer, compared to ceramics. This doesn't mean that we immediately jump, we say, oh, we need to remove all the metals, we will replace with a ceramic, we will replace with a polymer. No, metals have a number of good features also. So if we can fine tune top surface, that's a 5, maybe say 5 to 10 micron, or maybe little bit more. If we know the where it is a little higher, we can use any kind of material. Because here the tribology, we are using the word 2D only, the top layers. If you are able to really play with that, if you are able to really provide a very good surface layer on the metals, then metals can be utilized because they are in abundance compared to the ceramic, compared to the polymers. So they particularly this metals, they have a strong addition, and then because of that there will be higher wear rate, and then we need to really treat it properly. One way is that you increase hardness in significantly high level. You can see the friction comes down and wear comes down, but we need to learn those things. So another good point is say that what is the oxygen available in environment significantly reduce the adhesive degradation. So this is the beneficial here. Otherwise, we are little conservative that there should not be any oxide layer formation on the metal surface. But here, from a tribological point of view, we said that oxide layer really helps. So environment indirectly is helping us. However, understanding this provides some knowledge to us. Now, that knowledge need to be used if we are making some vehicles or some product for the space or for the vacuum situation systems where oxygen will not be available. That means oxide layer will not form. That means if we are using a metal without appropriate knowledge or in the environment, then the addition may be very high and the coefficient of friction can be more than 1, more than 1.5 also. So we need to really understand that. Now, as I mentioned, the hardness is, that's why we have written hard materials are less susceptible to adhesive deterioration or adhesive wear or adhesive friction also. So this is an important aspect. Now, what has been shown here, here environment is helping us, and whenever you can see the debris, and if you chemically analyze, we will find a number of oxide molecules in that. That means we need to really figure out how much is a metal and how much an oxide, and if oxides are more compared to metal molecules and the deterioration is much lesser, that will be a favorable situation. But how do we go ahead? Naturally, there is a need of the balance. What we say, rate of formation of oxide layer, how much time it takes to make a layer, and how much time it really takes to remove the layer. If a rate of formation of oxide layer is on a higher side compared to removal rate, naturally addition will be lesser. If rate of formation of oxide layer is lesser than removal rate is much faster, naturally addition will occur. So these are important aspects, and we need to think about appropriate treatment when we are trying to utilize the metals or maybe materials for the product design. Now let's understand a little bit more about adhesion. So here we are showing the adhesive wear mechanism. We say under load and relative speed, and assuming that there is a asperities which are deforming the material and they are removing the protective oxide layer. Again, if rate of removal of oxide layer is higher compared to rate of formation of oxide layer, then addition will occur. If rate of protective layer formation is more and removal rate is lesser, then chances of adhesion will be lesser. Well, in this case, what we are assuming that protective layer has been removed, and those removed part layer has been shown as a, we are treating this as a loose particle. So, in fact, this loose particle may act as a three body aberration, which will be covering maybe say after a few slides. But these loose particles, if they are soft, then they may act as a lubricant also. If they are hard, hardness is on higher side compared to parent material, then they will act as the abrating materials. So, we need to really think, and maybe I can show what I am mentioning about the loose particle. If you look at this thing, these are the abrasive, these are the particles. Some particles after removal they become soft, or they are like a lubricant. Some are really harmful for the we say the interface, and we need to remove it. So, here we are assuming now the addition has occurred and a formation of adhesive junction has happened. So, what will happen? Naturally, we need to push, we need to separate this two surfaces, and we know that already we have learned in lecture 3 that there will be addition junction and we need to break it. When you are breaking it, you can see that there is a material transfer happening over here. Material from this surface, maybe same assuming 2, and this is the 1, from 2 it has got shifted here or here. So, this is the 1 and this transferred material is related to 2, and a bigger scale we are showing here. In this case, a hard surface is taking material from a soft material. This is what we say soft material, blue color, green color hard material, and the transfer which has happened, we are not showing in a blue color even though it should be the blue color, but once it gets removed, then there is a possibility of oxide formation, maybe some sort of chemical composition. So, it may be slightly different than what we know the composition of the blue material. And we are showing here the one failed the ball which we have tested in a 4-ball tester. You can see here that top surface, it was a spherical, instead of point we are able to see some sort of circular area over here. Not only this, we are able to see some black color over here. That means material got displaced and melted, and finally again got converted to the solid. So, material was displaced from here to the here, and then it was in molten stage. After some time it appears something like this. So, the molten material is solidified, and that is shown as a black color. So, this is a material is getting displayed, and quite possible the material of this ball has got shifted to the other ball, and other ball material has shifted to here. So, there is a possibility. Now, once we do it, what is the really thing here? Projected area of one material tube. If it continues, it will be shown over here, then it will continuously keep rubbing against the surface, and overall you can figure out the surface roughness is changing. And in this case, quite possible both the material have a some compatibility. So, material is getting transferred from one surface to other surface. So, it is not only the 100% one's material is the softer material, having some sort of equivalence, maybe ranging from 0.8 to 1.2 hardness ratio. So, that is why the materials are getting transferred from both the surfaces. So, you are able to see there is a material deposition, material deposition, material deposition, and this is a bigger one. So, when the bigger material, the bulk material moves, naturally the clearance will be exhausted and the friction force will increase, and that has been shown here that you can see that this has bulged out, or maybe say addition has gone a much higher level, the bigger material or the bigger chunk has come. Now, what will happen, as there is no possibility of moving easily, and if we are applying a more torque, naturally this lump which has been formed, it will turn out to be a separate material, it will get detached from a parent material. So, separation of large lump from parent material, and then this will treat it as a loose particle, and that is what we say that even the addition is starting mechanism is additive wear, but quite possible after this we have the separated no, this lump material lump from material, then it may turn out to be a three body abrasion, or this particle will act or rub against other material. So we will learn little bit about this in maybe say after 3-4 slides. However, if I want to really summarize what I explain here, we say here, even if we look at the definition of the fracture, meaning of the fracture, it has been given a separation or disintegration of solid body in two or more parts. So this is a solid body, this is a solid body, and we are able to see this geometry which got separated from this. That means if wherever debris is getting removed from a surface, that can be treated as a fracture. So that's a new term. Many people are not convinced with this. However, we will be treating in our course that where debris is a fractured surface or fractured material from a parent material. Now, we see the wear phenomena, whatever we are studying with this addition, is slightly different than the friction, because we have a treated adhesive wear and adhesive friction also. But what is the really difference? The difference has been shown here, maybe stated here. We say the wear occurs over the time. It's not instantaneous. Friction is instantaneous. That means you will be getting friction values much faster, but wear requires little more time. Now this particle which has come out, it may have come out after 1000 cycle, 10,000 cycle, 100,000 cycle. Once the wear means the debris has been removed from a parent material, then it will be only treated as a wear. However, material getting transferred from one surface to other surface, generally we don't treat this as a wear. So removal of the material from a surface is treated as a wear, and that's why we say that there is a fracture and wear. There's a lot of commonality, and then we need to think whenever we do some sort of classification based on that. However, we will be dealing more about wear debris solely because that is kind of evidence that what kind of mechanism is really happening at the interface, and how do we really minimize that wear hits. So that will what will be covered in a lecture 18, that has been shown, that measurement of the wear debris is basically whenever there is a wear debris, we say it is a third body particle, is a 3D, it's not a parent material 1 or material 2, it has come out as a third particle or third material, and then we need to do experiments on measurement of the wear debris, and then we need to figure out what is the morphology of the wear particles. Morphology can be in terms of length, it can be in terms of perimeter, area, and other parameters can be decided. Now, if I do image analysis, I can really see whether images are really matching, or we can classify even wear particles in 6 category, 9 category. Of course, again there is a lot of research people are doing, and based on another length, perimeter and area, we can decide, oh, this is the fatigue wear, this is the adhesive wear, this abrasive wear. That can be done, but that will be dealt in the lecture 18, not in this lecture. Here we are trying to give some fundamentals, some challenges which are we need to solve using the sophisticated, or maybe say more mathematical oriented algorithms. Now, whatever I explained in previous slide, as I say that we are treating friction and wear in a similar manner, and then we can slightly divide. In this case, we have said friction because of addition, and here we are saying that even though addition happens, but unless the particle gets separated, unless it gets a fracture, then it is not a wear. So over here we will say wear means addition plus fracture. Now in here in the abrasion, we said very clearly particle will try to displace material of soft material. So that has been shown here. However, if the particles get separated, in the situation again the rupture can be counted. We say abrasion plus fracture. While in this friction case, we say instead of abrasion, we use a word plowing. That has been shown here. Now, new terminology which we have not covered earlier in lecture, and here is a hysteresis. What is the meaning of hysteresis? We are deforming, we are loading, and then we are unloading. Then these are the different things. Now this is we will be covering in this. Then another thing comes of fatigue plus fracture. Now this is a surface fatigue has happened, generally happens on the longer cycles, 10 to 6, 10 to 7 cycles, something like that. And we will deal in this present lecture about this also, and we will try to go ahead with a slightly different manner. Now we say friction and wear we know that is a causing a surface degradation, and surface degradation leading to the failure. So sometimes people say, I don't worry about which kind of mechanism, I need to just worry whether wear is a mild wear or severe wear. So that's why they use a word of mild wear or severe wear. You just tell us whether it's a mild wear or a severe wear. And what is the definition of mild wear? We say surface damage confined with the outer protective layer only. That means whatever the protective layer on the top, that is only getting the wear out, but not completely, partially, and quite possible before it gets removed, the next layer is getting formed on that. Or another word, we say the rate of formation of oxide layer, or maybe say some contamination layer or some sort of mild corrosion layer, is higher compared to the removal rate, right? So in this case the green is greater than red color. Coming to the severe wear, we say completely protective layer is removed, virgin materials are coming into contact, and they are abrading or adhesion happening, or some mechanism related to wear is happening. So that's why we say surface degradation within in bulk layer itself, that is inner of the material itself. The material rate, removal rate is much faster, and there's no oxide formation, there's no contamination formation. So in the situation what we say, this red color is a higher side, that removal of the rate of the oxide layer is on a higher side compared to removal of the formation of oxide layer. So this is a way classification happens. As I say, this topic is has been covered by many authors, many researchers, and there are number of books also on that, and our job is to summarize in a manner and then apply machine learning, so the subsequent lecture in much effective manner. That's the major purpose of the lecture. Now here what we are saying that this hysteresis and fatigue fracture, or that's what we say rolling contact fatigue, we are not covered earlier, and that's what we here writing here, that for rolling contact, hysteresis and contact fatigue are frequently used. And sliding is a one case, but this is a rolling case. So in the rolling case, these two terms are more frequently used, hysteresis and rolling contact fatigue has been utilized. Now one thing is that on in this particularly situation, on increasing hardness, a deformation will decrease. Even though in a sliding case, increase in hardness, wear rate reduces, but somehow in a rolling contact, this really helps more. Hardness, I will say that try to minimize deformation, whichever manner you can do. That the deformation is a lesser, that will give better results. So what we say here, the hysteresis loss and the mu r will decrease if you increase the hardness, and if the friction also will come down, wear rate will also come down if you increase the hardness. And that's why we are again certain that hardness is a correlated to the contact strength. That's a material contact strength. We increase the hardness, more contact strength increases, and that increases the fatigue life or service life of the product. So that is a required for our purpose. Now sometime people give a classification based on zero or measurable wear. What is the meaning of zero wear? Is something like a polishing wear. That's the improving the surface of the tribo interface. That means effectively specific film thickness will be on a higher side. So we should not use a word wear at all. It's a zero wear. It's a beneficial. Of course, we know very well that it will be the happening only during the running in time, and that's why we say running in time should be used properly, so that two surfaces they become comfortable with each other, and the wear rate comes down to almost zero level. Now other one is a measurable wear, where we are counting ultra mild wear, severe wear, moderate wear. That is a measurable. Now measurement can happen by weight loss or maybe volume loss. I'll prefer go to volume loss related parameters compared to weight loss. Reason being, there are many polymers, they contain water, and the water gets evaporated during operation even though there is a no wear, but water gets operated and evaporated. Then if you measure that, naturally it will show wear, which is not a right way. So better we look at the volume. However, when we talk about the volume, again irregularity comes. That's why the machine learning algorithms are required. How will you model irregular surfaces? I can say there's a plane surface, there's a hemispherical surface, there's a conical surface, but geometry changes drastically, then I can't measure where. That means I require x and y coordinates or x and y z coordinates, and I need to make a shape in algorithm itself. That's why we require more sophisticated algorithms for that. And in our earlier lecture, we say acceptable wear. We say whenever this wear constant or dimensionless wear constant is greater than 10 to minus 3, that means 0.001, then it is unacceptable. That means wear life will be much smaller. And then if you do not remember, this is a wear constant which we were teaching here. This is the dimensionless. We know that Newton and there is a Newton per meter square, and this is the meter. So it's a meter cube. That means volume should be measured in the meter cube or centimeter cube or mm cube or micron cube, whichever manner, and this k will turn out to be dimensionless constant. If it is a greater than 0.001, we will say wear is unacceptable, it should not be utilized. Now, as I said that ideal case, and what we were talking about the wear and wear coefficient. So I use in previous lecture I mentioned about the bathtub cup. Reason being, it if you look at the A, B, C, D, it is a bathtub. We take a bath in this particularly. So the bathtub, and then we say that maybe wear volume can be estimated either abrasive wear or adhesive wear, because they are covering almost 75% plus cases we can think about, and this is the wear constant, which is what we also mentioned in previous slide. Now this is what we are seeing the ideal case. So what is the meaning and why do I say ideal? Because if you look at the A to B, it is a decreasing, C to D it is increasing, but this portion B to C, this is a perfectly matching x axis, value is 0. That's an ideal case. That means once running in, final wear has come to settle down, and after that there is no wear at all. It is going to sustain a very long life, and after design life there is a possibility crack gets propagated, and once one crack is started, a pit formation occurs. After that clustering of the this pitting on the will occur, and we will say that the life is over and we need to replace. So this is an ideal case. But however, if there is a ultra mild case or mild case, moderate wear, you can see here the slope is increasing from maybe say this red color line, blue color line, dashed line, black line. So this is a worst case. We don't want this kind of cases. And if we want a good lubrication, of course we know the ideal case will not be there. We try to keep in ultra mild wear domain. So this is very important to consider, and then get a better results from this point of view. Now we discuss something about the hysteresis. Now we know that this is a part of the rolling friction, and you have seen you are able to see there is a ball or rolling ball on that, and this is a rubber sheet. So whenever the rubber ball rotates, sorry, this steel ball rotates on the rubber sheet, what will happen? In the front portion will get depressed, and back portion will get released. So this is a kind of the loading happening and unloading happening, and in this loading and unloading, whatever energy loss occurs, that is a frictional loss, and that's what we need to really figure out, what is the hysteresis loss in rolling cases. It's not that we will get always a single line loading unloading will be 100% successful, or maybe say we will get a straight line. It's not like that. there will be some losses, but this loss should be very low. And we say ideally coefficient of friction of a particularly rolling case, if you are keeping very high hardness, particularly we talk about something like a 62 HRC hardness of the steel balls and perfectly smooth surface. You look at the polished balls, they are very good, they have a mirror finish and they have very high hardness. In the situation, even coefficient of friction can be restrained or maybe restricted to 0.001, but keep in mind they are very sensitive towards the surface roughness. Now if steel balls rolls on other surface and that surface is also rough, naturally coefficient of friction will increase. So if the ball is rough, that's a problem. If surface on which the ball is rotating is a rough, again there is a problem, coefficient of friction will increase. And in fact if there is a surface roughness, then again what way we have learned abrasion and flowing, that will come into picture. It's not then hysteresis. Hysteresis is basically smooth surface deforming and retaining gaining the shape back. That's what we say that perfectly elastic and that too instantaneous. However, we know that it will not happen, and we are aware that every rubber material has a loss modulus. Metals which we generally use elastic modulus. While when we use a rubber, then we also use a word loss modulus, that means how much energy is going to be lost after deformation. So that is important, and this is happening finally in the dissipation of energy because of the loss of energy, or maybe say because of friction. Now that also can increase a friction or maybe internal temperature that can damage further and then can be a cumulative effect. So that's why we say rolling friction need to be maintained lower side. Whatever the material we choose, they should have a minimum hysteresis loop almost zero, there should not be any area enclosed in that, and then surface finish has to be very good. So again and again I'm bringing surface finish. Material has an impact, but surface roughness in my view has a much more importance compared to the material itself. Let me take an example of the rolling contact bearing, in that because we are talking about the rolling friction and the rolling contact fatigue. The same thing happened in the ball bearing. Here you can see here there is a cage, rolling ball, and then inner ring and outer ring. We know there is a, of course this curvature has been shown in much bigger way. It generally happens only 1% difference of the ball radius. Just to illustrate we are showing, and then this is also another interface. So you can see here there is a tribo interface 1, tribo interface 2, then cage also, then tribo interface 3, and then that is causing the friction losses into the rolling element bearing. Now we say that even though we are keeping material very hardness very high, and then there should not be whatever the load, there should not be any plastic deformation. Of course plastic deformation, that they also use a static capacity, and then they really do the measure and quote what is the plastic level and the which load it can sustain without going through the plastic deformation. And whatever the material they choose, they generally have very low hysteresis loss, and then far lower than 1%, and coefficient of friction they are able to maintain at the 0.001 because of the hysteresis. However, if there is a misalignment, again the coefficient of friction will increase. So it's not easy, and then we know that perfectly aligning the bearing we really require a sophisticated tool. That's where the industry plays more important role. When we do in academic institution, when we install the bearing itself, there will be some sort of misalignment. So coefficient of friction will increase, and it will really we say the give some signals which can be detected. Yeah, there is some misalignment. That's why we are getting the signals from a bearing. Now this is we say that we are using cage to avoid the rubbing of ball versus ball, but we know that cage itself will provide a sliding to the balls, and that is where the coefficient of friction will come. That's why we written that. However, the sliding friction occurs between the cage and balls, and sliding frequency is a greater than rolling friction here. So we are trying to retain the ball, so the load carrying capacity comes in a proper way, and we don't want to go with a many balls, because again what we say fully complemented bearing can be made, but that will cause a more friction also. And needle roller bearing is known for that. We keep a fully complemented, and the highest coefficient of friction, I think 0.0045, belongs to the needle roller bearing. Now, to reduce this kind of sliding friction, often we use a lubricant, and I say the NLJ grade 2 or maybe say NLJ 1 or NLJ 3, depends on what is the requirement. We use a grease lubricant, more often grease lubricant for the rolling element bearing. But if it is really required a centralized system, then we can go for the liquid lubrication also. Now, this lubricant is trying to reduce the friction. In addition, it really provides some sort of protection against the corrosion. So, that is also important for us. Now, when we are discussing this topic, we say rolling contact fatigue, that is what we are using in the short, the surface fatigue. And when I say that whenever we are using the mechanism adhesive, then fracture should be added, abrasion, the fracture should be added, fatigue, fracture should be added, because finally wear means a separate particle, loose particle, which is coming as a third body metal or material in this situation. So, surface fatigue in this case can be defined as basically kind of the pitting, which occurs particularly when there is a contact stresses are very high, and particularly it happens in a gigapascal. So, between the rolling contact, this stress level is very high, and then finally it comes out to be a small particle from a surface gets separated from a particle, so gets separated from surface, and that causes the fatigue failure. And now when we are saying that this term is a pitting, and sometimes people don't use a fatigue wear, they say pitting. The pitting especially result of the repeated high stress, high contact stresses. Now this what we are saying, there is a contact stresses who are creating a pitting, but in addition, addition to the high stress which is getting created because of the high load and smaller contact patch. In addition, the friction, sliding, lubricant, temperature and surface roughness also have a big greater impact. So, whenever we want in totality, we need to cover all these topic together, and that will provide a good results to us. Now, this is a picture has been shown which I analyze one rolling element bearing. You are able to see number of pits. So, this outer race has already seen or sustained 40,000 operating hours. That's why the pitting has happened and getting concentrated. You look at only this is the one portion of the bearing, and if you want to further rotate the bearing, it may sustain maybe say 500 more hours. In emergency case, we do also we rotate this outer ring by the 90-degree, 180-degree, so that it can really sustain more number of cycles. So there's a possibility, but maintenance is important, and then really carefully thinking how to rotate what angle, it will really be able to give a good result. So that's why they require a little more domain knowledge. Fitting, we are able to see, and it has sustained the life without any fracture. So many times people say that, oh, it can be reconditioned, but we know that reconditioning this big bearing is bit difficult. However, with advanced technology, that can be done also. Now, just to give a little more explanation of the fatigue plus fracture, whatever I say, we say even suppose there is a no load, variable load, but because of the surface roughness, the load will turn out to be the fatigue load, or in other words, almost every load in a real situation is a fatigue load, because we know there is a periodic motion, and we in a last maybe say lecture 2, we have already learned that this roughness is a periodic. We take a 5 samples and then we do averaging of that. So this is a periodic, and then when the next surface moves, naturally there will be ups and downs, and that's going to create some sort of fatigue or some kind of a change in the friction for change in normal load also. So this is almost every case in world is subjected to fatigue load. Just to illustrate in a little, maybe elaborate little bit more manner, what we have shown that the every surface has some cracks. Now, with a ductile material, with a brittle material, they will have some cracks. And then when we are loading applying a fatigue loading, that means we are compressing and releasing, subjecting to compressive force, and then subjected to and it will become release, then it will be subjected to the tensile load. What will happen that these small cracks which were initially there, they will get elongated in perpendicular direction, perpendicular to the applied load direction. Now slowly, because they are growing, quite possible the 2 3 cracks get merged together and become a big crack, something like that. Slowly it will move to the surface and whole chunk will come out, and that's what we the wear debris. Even though it is shown a bigger level here, but this wear debris can be even 5 micron size, or maximum size can be 5 micron. So we will study this in the lecture 18, provided some go results. However, what are the steps particularly for the fatigue wear? We say is a application of normal load the way it has been shown. At the contact point there will be some sort of plastic deformation per cycle, and then there will be generation of the crack or nucleation of crack, and finally it will come to the crack, which is a measurable, maybe say 5 say little bit more, that we can be really seen by non-destructive testing also. So we can see this kind of cracks. Of course these kind of cracks cannot be seen, it can be only guessed, while in this kind of crack can be seen in a non-destructive testing. If we are able to see, and then we are able to play and then take a remedial action, then even this kind of fatigue can be postpone, or maybe say linger to further, or maybe say life can be enhanced. Now this expansion of crack due to reversal of the stress has been shown, the extension will occur, and finally it will generate a particle that has been shown here. So this is A is related to this, B is related to this, C is related to this, and D is related to this. Now many books they show cracks propagation in this manner. We say there is an initial crack, I am trying to show from a side, this is a crack, and there is a stress concentration, and then if it comes to the some measurable size, then we will say crack has initiated, and then after that it goes to the propagation is, and then finally it happens a failure. Again we are talking about the fault, not a component. So this we have a more emphasis on the fault, but not on the failure. Most of the books they cover the fatigue failure, or they cover the fatigue fracture, and they indicate the failure. However, we are talking about the fatigue fracture in terms of the wear debris, which can be in even micron size. So it is not a complete failure, it is an initiation of failure, and we can take a remedial action on that. Just to illustrate, again I am trying to show there is a one surface, it has cracks inside, and then we have a sliding direction. Of course there will be normal load also. Now because of this sliding direction and the friction, shear stress will be induced, and we know that shear stress, maximum shear stress will occur just below, maybe say some thickness below the surface. It can be measured in terms of, it can be related in terms of the Hudson contact width. There's a possibility, but happens slightly lesser below the surface. As below the surface, and there is a normal stress, and because of that maximum principal stress will happen somewhere, and which causes on the crack to propagate and come finally to the surface. So these are there are theories which will justify this kind of reasons. Now coming to the why this material have already inbuilt cracks, you can see the ductile material have a voids, that itself can be treated as a crack. Even the ceramic materials, they have a granules, and they have a cleavages also. So these are the kind of the grain bond itself can be acting as a crack initiator, or maybe the nucleus of the crack, and that need to be elongated or will be elongated based on that. So that's why we now finally say that for this, even the fatigue, if it gives a particle which can act as a abrasion, which can act as a addition. So these three particles, abrasion, addition, fatigue, which overall play a major role in the failures, they can work together. Lead one failure, lead to other failure lead to the third failure. So they work together, and then finally, of course, somebody wants to find out only the root cause, then they need to go to detailed mechanism. Otherwise, they work together, and then almost in all situation you will find somewhere abrasive wear, somewhere adhesive wear, somewhere fatigue wear also. Just to elaborate whatever I mentioned here, now we see the top layer particularly. Now again here you can see here the undeformed layer, moderated deformed layer, highly deformed layer. And when the contact fatigue, the load is very high, and then top layer is under tension, under movement, or maybe say tensile stress, and that is a highly deformed in a sliding direction. So layers are getting deformed, and then there's a possibility of detachment of this layer also. So we need to really design this layer in a manner so that maybe even when we apply a coating, that the delamination should not happen at this level. So this is the important aspect. Now we see surface roughness play important role. Reason being, where we have already analyzed or covered in lecture 3 the wear coefficient, and then we say that above 60 degree only that is lesser than 1, and then we can see how the wear coefficient is decreasing with increase in a contact angle, or maybe say the cone angle. So there are three diagrams has been shown. One is with a 60 degree, one is a 100 degree, one is a 140 degree. When we are really changing the this cone angle or asperity angle, you can see the radiuses are also getting changed. And when radiuses are getting changed, even Hertzian radius also will be increasing continuously. As the Hertzian stresses continuously increases, that means contact area is increasing. When contact area is increasing, stresses will come down. When stresses will come down, naturally failure will be less severe. That's what has been shown, that if the asperities are better or surface roughness is not there, then the friction performance can be improved significantly. That has been shown in this case, and then you can see here particularly when the contact angle is lesser, shear stress also magnitude is on the higher side. Reason being, it has some relation with the normal stress also. So this is what has been shown, maximum, then lesser here. Just for a more illustrative purpose, and the student must have already covered something like cutting tool geometry also. We know very well when cutting tool has a very sharp edge, then the chipping will be happening, a material removal rate will be higher side. When it has a blunt edge, maybe say contact angle is on higher side, we have seen that the debris formation will be lesser, chip formation will be lesser. Same mechanism happens in the fatigue case. When we have this aspirate is having a sharp angle, naturally they will play slightly different manner, and then contact area will be much less compared to the blunt one, and then coefficient of friction will vary according to that. Now another one is abrasive wear. As I said, the abrasive wear, whether it's a three body abrasion, two body abrasion, there's a need to really think about that also. We see that two body abrasion happens because of asperities, and three body abrasion happens because of third particle should come at the interface. And many times we say adhesive particle finally will turn out to be as a wear debris. And wear debris, if it gets trapped into the interface, that will act as a third body abrasion, while two body abrasion asperities will be there. Now this can be this diagram already been shown in the earlier lectures, so I'm not going to cover again here, but what we see here depends on the asperity, whether it is really going for micro cutting. In previous lecture, on the previous slide, I showed that the sharp edges naturally will create a more the cutting action. So that's why we are saying the sharp particle or very hard asperities with a on this cone angle much smaller size, that will try to cut the softest surface. So naturally this wear will be severe, and that's why we say the surface roughness should be much lower, and even the asperities should have a very low a very high angle, or with a cone angle on this way. Coming to the fracture, because in this happens in this case particularly for brittle material, they already have some cracks which have been shown. It can be granular crack, it can be crevices, or can be the boundary, or that is where the already established cracks are there, and elongation or maybe propagation will not be that much problematic. So that happens in there, and then we finally it will lead to the surface fracture, creation of pitting, or creation of pits on the surface. That will be the more harmful. Coming to the other two kind of abrasive wear mechanism, one is what we call as a micro fatigue, another one is the removal of the wear grains. Again, the removal of wear grain is for the brittle material, because they have already grain boundaries, and that is very easy to separate. That's why many times we say that we should use a homogeneous material, instead of using heterogeneous material, because heterogeneous material will have much more grain boundary, much more interfaces, and that will be easy to abrade compared to the ductile material or compared to the homogeneous material. So that has been shown here. You can see the abrasive where the surface is the spirit is blunt, and it is making a groove in this material, and there is also the debris which is not yet got removed. It is getting pushed, material is getting displaced. So it can be in 1 ton or maybe 1 cycle, it can be after 100 cycle, 1,000 cycle or 10,000 cycles. So that is depending on the real and then the strength of material and the geometry of the asperity. So this has been shown in the similar manner where say the grit is a basically particle, and it can be subjected to micro fatigue, or it can be subjected to the, because when we go for the this brittle material, already cracks are there, and then finally a complete grain will come out of the surface. That also can be done. Now when we using this kind of material, we see it can take several passages, and it's not necessary immediately it happens. And in first slide, first or second slide, I already say basic difference between friction and wear is that friction is instantaneous, while wear is a time taking. It will take some time, take some cycles to produce a wear debris particle. Now whatever we have studied about the abrasion, very similar mechanism are erosive wear and cavitation wear. Erosion wear is basically where the third body comes with a velocity, and we talk about the impact. It has already kinetic energy. The same thing in cavitation. The bubble gets burst. Naturally, it will have a lot of energy of the liquid, and it will burst on the surface. So similar kind of mechanism happens in erosion and cavitation. You're not dealing much. Of course, equation will change for each case. Model will change for each case. But we are trying to generalize in a manner so that we can treat it in proper manner. The two body abrasion, then we say 30 body abrasion. Question comes, which one is much more harmful? In my view, the 3 body abrasion is much more comfortable compared to the 2 body abrasion. Reason being that most of the time particle will roll. So it is not a sliding. While 2 body abrasion, it is a always sliding happens. While in third body, it will keep rotating also, quite possible 80% energy will be taken away in a rolling action. So that's why I say that sliding effect is lesser than 20%. Many times two body the wear coefficient just giving some value. It's not that it will be always like that. It's just a comparison purpose. It can be 5 into 10 raised to minus 3 to 50 into 10 raised to minus 3. That's what I'm just giving some figure. It can be higher, can be lesser. But if the two body abrasive wear coefficient is something like that, three body will be 1 order magnitude lesser. That means it will be 5 into 10 raised to minus 4 to 50 into 10 raised to minus 4. So that's important aspects to think about. Another thing, when three body abrasion, I say that where debris comes out. Now if where debris is a soft, then it will be helping as a lubricant. But if on the third body abrasion particle is coming out to be as a hard, it will push. However, there is a possibility it may form something else also. So there is a possibility that adhesive wear leads to the abrasive wear, and that quite possible abrasive wear leads to the adhesive wear. So these things will happen, and that's why I say in totality, in overall, most of the wear mechanism happen together. It's not a very clear cut mechanism unless we do some use of some tribometer, and under some control condition we create a mechanism. Then in the okay, but in the practical situation, mostly the wear mechanism will be working together, and then finding root cause really will be difficult. So that's why many times we give a overall generalized solution compared to the going to the complete solution of that. Now what we see that anytime particle size is bigger than the available clearance, particularly for the bearing case, then we really require to filter those particles, otherwise the damage will be much more severe. And this is happens particularly in the particle, we say that materials are soft. If the particle get embedded in a soft particle, then the three body abrasion will also be acting as a two body abrasion, because already it got form the formally established in the soft material. So two body abrasion may lead to three body abrasion, three body abrasion may lead to two body abrasion also. So this is a way the things keep working, or working together, maybe say one wear mechanism leading to other mechanism, or other mechanism leading to third mechanism. And there are many examples of this three body abrasion. You take any earth moving equipment, you will find, you take any slurry pump, you will find this kind of three body abrasion. Drilling or pneumatic transportation of the powder, three body abrasion is common. So there are many examples particularly related to three body abrasion. Now if I try to summarize all this, what we see, already we have learned the adhesive wear, it is easier. Coming to the abrasive wear, two body abrasion we covered, three body abrasion we covered. And then we said also that and particularly when in ceramics, homogeneous phase is always preferable compared to the heterogeneous phase, because they will have much more grain boundaries, and then abrasive wear will be more damaging. Another one, we say the softer material and harder material ratio, hardness ratio particularly, should be in the range of 0.8 to 1.2. It should not be more than or much lesser than, because the abrasion will be much higher side. So if you want to keep a control on abrasive wear, then we try to keep this hardness ratio 0.8 to 1.2, otherwise more wear will occur. And then we were trying to say that abrasive wear involves micro fatigue, micro cutting situation. Brittle materials are weaker, having weaker grain boundary. That's why the grain separation occurs in those situations. And abrasive wear, whatever we understand, is like a erosive wear, like a cavitation wear. Of course, equation will change, parameter will change, but mechanism of removal will be more or less same. So that's why we don't want to deal in a detail about erosive wear and cavitation wear, but mechanism will be more or less safe. So I'm coming to that was the last slide. In this situation, we say that there are so many wear mechanism. What do we do? So there's a now new concept comes from the wear map again. People say it is not very accurate, but at least it can give the glance. Now they do the material, one material versus another material on some sort of a tribometer. Here we are using the pin on disc, the tribometer, and this wear map comes in with a parameter sliding velocity and bearing pressure, or which is can be measured easily. You can see we are coefficient ultramite 10 is to minus 9, 10 is to minus 6, 10 is to minus 7. As the sliding direction it is increasing, that we are finding the coefficient is decreasing in the situation. Sorry, and the coefficient is increasing this side, and when we go vertical, coefficient is decreasing. That means as the pressure increases, coefficient will be wear will be much higher side, and that's why the wear coefficient comes down. And this you can see here 10 is to minus 2, 10 is to minus 3. As the pressure increases, wear coefficient and say value increases. As the sliding speed increases, wear coefficient decreases. And overall combination, you can see here the boundaries. That means there is a transition from one wear domain to other domain. So that has been shown in a wear map. So if I try to highlight whatever I mentioned, say, and in the person who is operating, they can measure easily pressure and velocity, and there are so many wear maps in the literature. We can digitize, we can make a complete tabular form also. And then particularly this field line, this has been shown, the black color line of the field boundaries, they run along with the two mechanism, as I said, the transition from one mechanism to other mechanism. And then this is not really distinguishing oh, it is a abrasive wear, it is adhesive wear, it is a friction the fatigue wear. It gives a what is the value of their coefficient, and if wear coefficient or is lesser, we are comfortable. Wear coefficient on higher side, we are not comfortable. We need to really take appropriate care. And many times we say we learn three things. What is the rupture time of the oxide layer, top layer, how fast it is getting ruptured, and then what is the reoxidation time, and what is the formation rate. Initially I shown the green color and red color. Red color was a rupture rate of rupture, and green color rate of formation. So same thing comes from this also. So what is the time available and how we are going ahead. Now this is I say the last slide, and with this I say thank you for attending this lecture. Thank you.